Good morning students. Today we are going to see about problems on Castiglione's theorem. So before that we have to know what is Castiglione's theorem. So Castiglione's theorem is stated as follows. If capital U is the total strain energy of any structure due to the application of external loads capital W1 comma capital W2 comma capital W3 dot capital Wn at points capital A1 comma A2 comma A3 dot capital An respectively in the directions capital AX1 comma AX2 comma AX3 dot capital AXN and due to couples capital M1 comma M2 comma dot capital Mn at points capital B1 comma B2 comma B3 comma dot Bm respectively. Then the deflections at the points capital A1 comma A2 comma A3 comma dot An in the directions AX1 comma AX2 comma AX3 comma dot AXN or dou u divided by dou w1 comma dou u divided by dou w2 comma dou u divided by dou w3 comma dot dou u divided by dou wn, and the angular position of the couples are dou u divided by dou m1 comma dou u divided by dou m2 comma dou u divided by dou m3 comma dot dou u divided by dou mn at the respective points of application. Okay, so this is Castiglione's theorem. Basically Castiglione's theorems are used in the following cases, like to determine the displacement of complicated structure. So next, to find the deflection of beams due to shearing or bending if the total strain energy due to shearing forces or bending moments is known. Okay, so last one, to find the deflection of curved beams and springs. Okay, so here the formula for finding the deflection under the Castiglione's theorem condition is the deflection delta equal to integral capital M divided by capital EI into dou M divided by dou W dx. So here deflection delta is nothing but deflection is defined as the vertical displacement of a point on a loaded beam. Okay, so now let us move on to the problem. So first, using Castiglione's theorem, obtain the deflection under a single concentrated load applied to a simply supported beam as beam shown in figure. Capital EI equal to 2.2 meganewton meter squared. We know that what is simply supported beam. A simply supported beam is the type of a beam that has pinned support at one end and roller support at the another other end. Okay, so here we have the beam is a simply supported beam and the EI value is 2.2 meganewton meter square. Okay, so here we have the simply supported beam is span AB, span ACB. Okay, so span AC distance is A to C distance is 3 meter and C to B distance is 1 meter. Okay, here the point load at C is 60 kilonewton. Okay, so first we have to calculate the reaction value. So first reaction at A point, so that is reaction at B, so we have to consider from the A point the reaction value. Okay, so first RA into whole distance 4, 3 plus 1 meter 4 equal to, here the point load is 60, but we have to consider the 60 kilonewton point load is W, so we have to use the W. So here which means here W equal to 60 equal to W. Okay, so RA into 4 equal to W into 1 meter, so C to B 1 meter, so W into 1, so RA equal to W divided by 4. Okay, next consider a XX cross section at a distance from at a distance x from A. Okay, so the distance A to xx cross section distance is x. Okay, so here moment we know that moment formula, load into distance or reaction into distance. Okay, so moment at x is, that is mx equal to ra into x. Okay, minus w, here w 60 equal to w. Okay, so w into x, known distance x minus 3. Okay, so the moment at x value equal to wx divided by 4 minus w into x minus 3. Okay, we know that deflection formula for Castiglione theorem is delta equal to integral m divided by ei into dou m divided by dou w into dx. So we have to calculate the dou m divided by dou w. Here dou m divided by dou w for the moment at x value is x divided by 4 minus x minus 3. Here the w value, we have to differentiate the w with we have to differentiate the m value, moment at x value with w. So here the w value is 1, so we can get the dou m divided by dou w equal to x divided by 4 minus x minus 3. Okay, so we can substitute the dou m divided by dou w value in delta formula. Okay, so we can separate the constants from the variables. So delta, here delta equal to 1 divided by a into integral. Here we have the limit is 0 to 3 for a c span. Okay, so 0 to 3 into w into x divided by 4. Again we have to integrate the wx divided by 4, that is so after the integrate we can get the w value is 1, so x divided by 4 into dx plus again another again we have to consider the whole span. So 1 divided by a equal to 3 to 4. 3 to 4 means c to b. So the limit is 3 to 4. Okay, the lower limit is 3, upper limit is 4. So integral 3 to 4 wx divided by 4 minus w into x minus 3. Okay, so again we have to integrate the wx divided by 4 minus is x divided by 4 minus x minus 1. Here the w value is after the integration we can get the w value is 1. Okay, so we can get like this. So after the here the x divided by 4 minus x minus 3 values like a minus b whole squared formula. So we have to we have to apply the a minus b whole squared formula. After we have to applied, we can get w divided by 16ei into integral 0 to 3 into x squared dx plus w divided by ei 3 to 4 x minus 4x plus 12 divided by 4 whole squared dx. Okay, so here after the integration we can get the x squared dx value is x cubed divided by 3, upper limit 3 to 0. Next here span CB, we can get the x squared minus 8x plus 16 dx value. After the integration we can get x cubed divided by 3 minus 8x squared divided by 2 plus 16x, upper limit 4, lower limit 4 3. Okay, so after the substitution of upper limit and lower limit, we can get the delta value is 9 w divided by 16ei into 1 plus 0.33. So that is 0.75 w divided by ei. So here w value is 60 kilonewton. So 60 into 10 to the power 3 Newton divided by ei value is 2.2 into 10 power 6. Okay, So after the substitution of WEI value, we can get the delta, that is deflection value is 0.02045 meter or 20.45 mm. So this is an deflection for a simply supported beam. Okay, thank you.